Today, I'd like to talk about our recent work on the computation of the quantity called entanglement of purification, which is a kind of a generalization of von Neumann entropy to mixed state. There are so many different extensions of entanglement entropy to mixed state, but this is just one of them. And I'd like to give especially a holographic description of this quantity. And so this work is based on this preprint, based on the collaboration with Koji Umemoto. And I'm going to mainly talk about this paper. And this paper has an overlap with the paper by another group, Nguyen, Dr. Harbash, Zaratel, and Brian Swingle. And also, I'd like to give also report a very modest progress of computation of this quantity in free quantum field theory, and based on the collaboration with Alpan Bhattacharya and Koji Umemoto. So let me begin with the introduction. So this is highly motivated by this ADS-CFT. And ADS-CFT provides us a very interesting way to realize some geometrization of dynamics of conformal field theory. So of course, quantum field theory is very algebraically complicated, but it gives some very nice, if we look in a geometrical way, we have very simple interpretation in terms of supergravity and so on. And one manifestation of this geometrization is to look at the entanglement, quantum entanglement of quantum field theory. And roughly speaking, we have in current knowledge tells us that quantum entanglement of quantum field theory or conformal field theory is roughly equivalent to the bulk geometry, metric and so on, and topology and so on. And so if we compute this, especially the one expressed quantity, we can compute this entanglement entropy. So entanglement entropy is minus plus rho log rho. This von Neumann entropy we define in this way. So we have some quantum field theory, which is situated the boundary of anti-de Sitter space in the context of ADS-CFT. But anyway, we have some CFT here, and we focus on particular region A, and we trace out the other part. And then we can define some reduced density matrix for rho A, and its von Neumann entropy is entanglement entropy. And holography tells us that this entropy is actually interpreted as the area divided by 4G Newton, like Bekenstein-Hawking formula, but this is a sort of generalization of Bekenstein-Hawking formula for black hole entropy. So this is no longer black hole, but the area is defined for surface, minimal surface, which end on the region A. But we have to impose this minimum area condition, but once we've done that, then we can compute the area and divide by usual constant 4 times Newton constant. That gives entanglement entropy in a dual conformal field theory. So this to see some geometrical aspect is one explicit example is strong subrelativity. So the strong subrelativity is a very important property of quantum mechanics and quantum field theory. For example, it is used to prove C theorem, like Horacio and Marina's work, famous work of C theorem, and also generalization of higher dimensions. And but the strong subrelativity can be easily seen in holography. And so this is a simple picture. So we have a region A, B, C, and strong subrelativity tells us this inequality. So A union B, we compute the entanglement for A union B and B union C and sum up, then it's always greater than this combination. But this is obvious from this picture. So we have A, B, C, and A union B corresponds to this minimal surface area of this surface, and BC is this surface. And we can combine this way, so that we can call this another surface which covers ABC, and this is one more surface covers B, and this is definitely greater than surface which really realizes minimum condition, minimal surface B times plus ABC minimum surface. It's obvious, and opposite. This is one more, but that's equivalent inequality. It can be easily derived. So, but anyway, that way, so algebraic relation in quantum information theory can be interpreted as some geometrical property, some generalization of triangle inequality in geometry, and so on. But here, in my talk, also one more important inequality is actually is given by this. This is worked out by Hayden, Hedrick, and Maloney 6 years ago, or 7 years ago. And so this is some inequality which is satisfied by mutual information. Mutual information, IAB is defined this way, just linear combination of entanglement entropy. So this is a measures roughly correlation between A and B. And so using some similar trick, like geometrical trick of minimal surfaces, we can prove this quantity is always negative, this linear combination, ABC and ABC and minus sign and ABBC. But you can combine by using mutual information, you can simplify this expression equivalently. So this is a correlation between A and union BC, and this is always greater than the sum of this. But however, this is we can easily show this from holography. But however, this inequality is not always true in general quantum systems. And for example, if we look at the massive free fermions quantum field theory, this is we can find this is actually positive. This is by Cassini, also, and Reuter's work. And so that way, so this is a very special. This means that holographic CFT, the CFT which has a holographic dual, has a very special property, namely this positivity of this, so negativity of this I3. This is called tripartite information, and this also plays in my some important role later in this talk. And this property also leads to the Kadoni-Linden-Winter inequality. This is some more sophisticated version of strong subadditivity, and as well as also some inequality called strong superadditivity. I'll come back this later. So the another issue which we can find some interesting geometry in ADS-CFT is tensor networks. And so quantum state in the ground state of conformal field theory or some critical spin chain, it's very, very algebraically complicated. But if we want to capture it in a geometrical way, one way to do this is to look at tensor network, which means that we have some quantum state which realized at the boundary, but by contracting tensors inside the bulk. So this is nothing, we are not using any holography, but just come from technical reason. So we just want to write wave functional by contracting indices. And then we naturally encounter this extra dimension holographic direction. And we can evaluate the entanglement between some region A and region B. So that by counting number of intersecting bonds, intersecting links, because each link gives a 1 bit entanglement, roughly speaking. So roughly this length gives a nice measure of entanglement. And so there are different choice of this gamma A, which is this region A, this subsystem A, and this subsystem B. And we can choose this way, but the minimum one gives the most optimized evaluation of entanglement. If we can go a little bit detour, so many times or something, then that's overestimate entanglement. So this minimization also appears here. So this has a nice matching with ADS-CFT. And so by using this idea of tensor network, it's quite easy to imagine that this emergent space-time from entanglement. So this, in the context of tensor network, this is proposed by Brian Swinger, and as a black hole Sanford and generalization will be conjectured by Ramston and many talks. And this is I mean my origin of it from Qubit idea. And so, but in this talk, we'd like to present a new conjecture which generalizes this this holographic computation of entanglement entropy. So this is my content. So first, I'd like to brief review of the idea, so-called entanglement wedge. Nowadays, people heavily use this. And now we go to this quantity. I'd like to introduce this quantity, entanglement of purification, and then go to the holographic computation. This is our proposal. And we'd like to give some also evidences why this proposal is true. And also would like to give some heuristic derivation of this quantity by using tensor network analysis. And so I also would like to finally report some modest progress about computation of entanglement of purification in free scalar quantum field theory with lattice discretization. So let me go to the just brief review of entanglement wedges. So there are so this is the idea of this correspondence between some subsystem in CFT and subregion in the bulk. So this is we have some region A here, and the other part is B. But we would like to focus on reduced density matrix for region A. This is a CFT reduced density matrix, and what's the dual to this in the bulk gravity. So the answer is this reduced density matrix, which corresponds to this region, which we call MA. This is also, I call this also entanglement wedge, MA. And which is MA is defined by the region surrounded by this region A as a boundary of ADS and bulk minimal surface gamma A, which I introduced just before to compute the entanglement entropy. So anyway, this surface, we take actually, here we naively assume simply assume some time, static space-time, and we just take some time slice. universal time slice. And this is the surrounded area is called MA, and the density matrix for this region is a correspond. We have correspondence between rho A and this rho MA. So there are many evidences for this, and starting from this HKLL analysis and up to recent discussions using error corrections and many sophisticated ideas. I'm not going to details about this. We're going to assume this. So we have a nice correspondence between subsystem in CFT and sub-region in the bulk. So we are focusing on this actually entanglement wedge later. So, but we have also covariant definition of entanglement wedge. It's more originary. So if in a time-dependent case, we have to be very careful. So there are no natural time slice. We have to define some geometrical object in a covariant way. So this is a region A, and we can always associate some gamma A. This is an extremal surface, covariantly defined. But there are no way to precisely pick up some particular slice or a particular region which sits between A and gamma A. But if we choose one of them, and we can talk about domain of dependence of this region, and that is universal. So this is the original, more precise definition of entanglement wedge. But in our argument, we are focusing on mainly on static system, static excited state, but the static system. So we are taking just time slice and just call this MA is this region MA is just an entanglement wedge. But it is possible to extend our argument in more time-dependent background. But I'm not going to detail. So now our main interest is to understand the physics of this entanglement wedge. So especially we look at the case, there are interesting cases where we have some two subsystems. So we have a region A and region B, and we talk about entanglement wedge for A union B. If they are separated, A and B are very small and they are separated, this minimal surface actually which covers A and B is disconnected, but they give the exact minimum of this entanglement entropy for A union B. So there are some connecting surface, but they give a larger area. So entanglement wedge for this case is just the union of MA and MB, and they are disconnected, so not that so interesting. So whatever mutual information is vanishing at the leading order of 1 over n expansions in square order. But if we look at the other case, A and B is very large and they are close to each other, then they are actually connecting minimal surface, which gives a smaller area compared with gamma A plus gamma B. So this case, entanglement wedge is just this union, this region, AB. This is connected region. And then, so we are focusing this case. And the first case is we just get the trivial result, just entanglement purification 0. But we are focusing this connected case. And the mutual information also non-zero, this case. And then natural quantity, geometrical quantity, we can define for this geometry is obviously this minimum cross section, which separate region A and region B in the bulk region and bulk region B. So we are looking at minimum cross section that measures amount of connection between A and B. So this is sigma AB, and this minimum surface divide MAB entanglement into A side and B side. So we focus on this quantity, and then so it is quite we are attempting to define quantity defined by this just area divided by 4G Newton. Always this appears because the connection to black hole entropy and so on. So this area of this minimal cross section divided by 4G Newton, and this it is natural to expect this quantity has some very nice interpretation in some quantum information theory, which I would like to going to give. But this is anyway, we define this quantity to be entanglement wedge cross section, it's obvious name, and for which is a quantity for defined for rho AB. Rho AB is a reduced density matrix. We trace out the other part, and rho AB is exactly dual to this entanglement wedge. So this quantity should only depend on rho AB, and this is simply defined by area divided by 4G Newton. And then, so our conjecture is like this. I will explain some evidences for this, and also definition of this quantity. But anyway, what we want to say, this entanglement wedge cross section is equal to the quantity which is known as entanglement of purification introduced by these people, others, in quantum information theory, 2002. And which also only depends on rho AB. And this is a kind of measure of correlation between two different subsystem A and B. And when rho AB is a pure state, if we assume this is just pure state, just pure wave function, then this quantity is just gives entanglement entropy. Just this quantity is just reduced to von Neumann entropy. So that case obvious. Also, entanglement cross section is naturally reduced to just minimal surface in this case. So this is obvious relation which we know already. So now I'd like to first introduce this quantity, and I want to explain some physical interpretation and some quantum information theoretical meaning. So this name shows this we need a purification. I think many of you already very much familiar with this, but just for definition, I'd like to introduce purification. So this is we have some given density matrix for some Hilbert space which called HC, C Hilbert space, and rho C is given by this mixed state. We can always diagonalize it this way. And we can always describe this state as a pure state by adding extra Hilbert space. We can, for example, prepare the same dimension, same size Hilbert space, HD. So that case, we can just prepare this wave function is just defined. This is pure state, but just sum over these i's and square root lambda I. And then we trace out this subsystems D, then obviously rho C, reduced density matrix precisely reproduce. This is the same as Sommerfeld double and many things. But the important point, there are infinitely many different ways to achieve this, depending on this basis choice. So that has some very important meaning. And then, so by using this, we can define this quantity entanglement or purification, which just I write it EOP. So consider all purification psi, which is correspond A tilde, B tilde. We add Hilbert space HA tilde and HB tilde. This is the extra Hilbert space, which, for example, like analogous to this HD. HC is here, sorry, HC is like AB. This is like C and D. So we add extra Hilbert space and purify. This is always possible, but the problem is that we have infinitely many different ways to achieve this. But anyway, let's assume such a purification of this mixed state rho AB. Then, anyway, we compute von Neumann entropy for AA tilde. So we can decompose AA tilde as one group and BB tilde as another group. And this is a pure state, so we can use this entanglement entropy as a good estimation of the quantum entanglement. So anyway, we define this, but problem is that this is really depends on how we purify the system. So we take a minimum or all possible purifications. But of course, we always keep this condition, rho AB should be always achieved by tracing out H. Under this constraint, we take a minimization or possible purification. And so it is obvious because of this property, this is always positive. And if this is zero, actually entropy is zero. So it's really, just direct product state. So this is a quantity which we'd like to consider in this talk. So this has a number of interesting properties worked out in this paper. And so most of them come from a strong subrelativity by hooking up some inequalities. So first one is, in general, this is bounded by entanglement entropy. And if this is pure, then obvious, as I mentioned, this is just coincides with von Neumann entropy. This is obvious from the definition. And so if this quantity, this is actually very important. This quantity is always bounded by half of mutual information. If the total space is pure state, this is the same as von Neumann entropy. So this is number of EPR pairs which we can produce. But it's even for mixed state, this is always bounded by half of mutual information. And also one more stronger condition like this. When we have a BC, this means B is like B union C. So we are talking about correlation between A and BC. And if this is a rho ABC is pure, actually we have this inequality. This is actually opposite to the inequality which we expect for entanglement measure, which is called monogamy relation. This is actually opposite, so it's called polygamy relation. Which has this inequality. It's always true. And finally, this is extensive. This is like mutual information. This is extensive. So if we increase the subsystems, then this quantity gets larger. This is quite intuitively natural. So these are all these follow from strong subrelativity. And so then I'd like to go to the operational interpretation of this quantity. But this is a very important idea in quantum information theory. But before that, I'd like to quickly review what happens for entanglement entropy, for what's the operational interpretation. So then this is basically this comes from the LOCC process, which probably familiar with many of you. And so we have set up some, anyway, anyway, A region A and region B. So this is like HA is factorized HA times HB. This is a starting point, and we would like to measure entanglement between A and B. But here, so that we can act some operations, which we can, so A and B, we can imagine A and B are far apart. Then we can do some, we have some each separate laboratories. We can make some quantum operation for A and B independently. These are local operations, projection measurement and unitary transformation. But if they are far apart, it's difficult to do some quantum measurement between them. So we do some only classical communications, like sending information by telephone or internet. So this is a classical communication. And these two guys are combined, and this is called LOCC. And this is allowed operation. This is assumption. We assume this we can only allow this LOCC operation. The basic example is well known. This is a quantum teleportation. So quantum teleportation, we need this both of these two. Measurement and quantum measurement, and also sending information to the other side. So this is what we'd like to do is like this. So we start with some originally very complicated entanglement between A and B. But using this LOCC, we simplify entanglement so that only entanglement comes from EPR pairs. EPR pair corresponds to maximally entangled pairs. So this is actually possible for pure state. This is a very famous theorem in quantum information theory. So this is a way how we can define this entanglement entropy as a measure of quantum entanglement. So this, so let us introduce following two quantities to measure quantum entanglement. First one is an entanglement, so-called entanglement cost. And this is the number of EPR pairs needed to create rho AB via LOCC. So this definition can be also followed. We can use this definition for mixed set. Rho AB can be any mixed set. And by using the LOCC, we want to convert this some number of EPR pair to rho AB, but the minimum amount of EPR pair which we need to prepare is an entanglement cost, and the entanglement distribution is opposite. So number of EPR pairs which we can create from rho AB by LOCCs. And the interesting thing is just a very famous fact is that for pure state, these two guys actually coincide with each other. So this is so these guys to coincide, so we can think this is a unique definition of entanglement, and this is it coincides precisely with von Neumann entropy. So pure state story is very simple. So this is the reason why we can just trust this formula and claim this is a quantum entanglement, and so on. But for mixed state situation, it's very complicated. So in general, of course, obviously, entanglement distribution is always smaller than cost. This is obvious inequality, and so these two, both of them has a nice measure of entanglement. So that means there are so many possibility of entanglement measure which sit between these two guys, and indeed there are many. And so if we just pick up famous one, there are many. But for example, it's squashed entanglement, and also entanglement of formation, and also ER, which is called the relative entropy entanglement, and so on. So for each of them, it is a very interesting question to ask what's the holographic computation of each of them. But actually, so we are looking at a little different quantity here. So now I come back to this quantity, so-called entanglement of purification. So this is actually equal to the entanglement cost for LOQ process. This is different from LOCC process. But this is anyway essentially same as the idea of entanglement cost. So this LOQ process is a local operation plus small number of communication, classical communication, small number of communications. So it's a really little bit restricted set, but it's some. Essentially, this says that essentially this is just a local operation. And so anyway, so this quantity, if we don't care about so much infinity here, so this is some more sophisticated part of this definition. But this is basically EPR number of EPR pairs needed to create rho AB via LOQ process. This coincides with the definition which I gave here, minimization of this entanglement entropy. So anyway, so this way we can define this quantity, and then we can, because this definition involves some minimization and so on, it's very easy to derive some inequality. This is quite mathematical computation. So if we look at this EP, this is quantity which we're looking at. Actually, we can find this is actually larger quantity than the other guys. So it is usually entanglement major sit between ED and EC. For example, one of the sophisticated quantities, flushed entanglement, really sits in between. But another quantity, so the entanglement of formation is a little bit outside, but essentially same. But EP is a little larger. So in that sense, unfortunately, but this is not entanglement measure. But however, this is a nice measure for correlations, and still have some. Also, this still have some operational meaning. So this is anyway. This is yes. But anyway, roughly speaking, we have LOCC, so it is interesting to ask what about just LO. This is a basic issue. So if we kick out essentially CC, then what happens? Small number is actually, so actually to precisely define this, we need to take a copy of the same state, and the number of communication should be smaller than this copy, which we call n. It's much smaller. So yeah, thank you very much for the question. So anyway, so that way this sits a little bit larger. But anyway, in the end we find, so originally we wanted to somehow think about some holographic dual these quantities, but this turned out to be very difficult. So far we don't have good understanding. But somehow this is easier to understand. This is the honest reason why we're looking at this. But this is still interesting properties. Also, this has a very simple connection to entanglement entropy, as this definition shows. Yes? Yeah, that's a good question. But we have to allow all possible purifications. In general, that purification space can be infinite. Then it's quite, I mean, not so easy. But in the end, I would like to give some recent result of our analysis for free scalar theory. And that case, somehow, because we can restrict the Gaussian wave functional, so this computation gets easier and just confined in a finite Hilbert space dimension. But in general, I think it's quite difficult. Yeah, I think that's very interesting. I mean, most important, actually. So how we can proceed this more. But anyway. And so, okay, so now I'd like to holographic computation. So to test, anyway, so we could claim this is actually equal. So we have to first confirm the properties of this entanglement of purification. So we had some 5 different properties. This is known so far. This 5. So I would like to confirm this, all of them. So first one is obvious. So this is the minimal cross section. This should be gamma A area should be much larger. Actually, this is even finite. This gets to infinite. So this is finite. And if rho AB is pure, then so if rho AB pure, that means AB, and there are no other place to trace out. So just gamma A gives a minimal cross section because I mean because entanglement wedge is whole region. So cross section is just this, and this trivial. And so property we go to this inequality. So this is a non-trivial inequality, but this can be found by using sort of triangle inequality. So we have this gamma A is here. So gamma A is here, and this is the AB. So this region is the entanglement wedge. They are separated by this minimal cross section, sigma AB. And we call this is the tip of minimal surface at the end. So gamma A, B, A1, B1, and A2, B2. So that's case we sum up this length or this area. It's obviously greater than gamma A. So obviously we have this inequality and similar inequality for B side and just sum of them. And then we get this inequality. So this means that this is a mutual information. So and we have a factor 2. So half of mutual information is always smaller than this quantity which we are looking at. And this is really coincide with this inequality. And this is independent. This was earlier. This was found by Friedman and Hedrick in the context of bit threat analysis of holographic entanglement entropy. And so we use this inequality turns very important. Also, this is also important in bit state ideas. And so then we go to the one more property. So this inequality, but this actually follows from monogamy of mutual information. This is only true for holographic theory. But anyway, so once we assume this, then using this we get this inequality. And property 4 is about this polygamy of this. When we assume ABC is pure, so it's like pure, ABC, and this inequality is false, but this is true. So because this red one is always greater than green plus this blue one. So holographically, these are all perfectly. We can confirm these properties. Sorry, one more thing. One more thing is extensivity. But for this, we can use this entanglement wedge property, entanglement nesting property. When C is larger than D, then corresponding entanglement wedge is has a monotonical size, monotonically increasing. So MC is always greater than MD. So if the ABC is include AB, of course, but then this is true. So this then cross section also, this guy gets larger. So this automatically follows. But there are one bonus for this holographic construction. So we can look at some inequality called strong superadditivity, which is actually defined by this. This is not actually known that it is known that this inequality is not always true. There are counterexamples known numerically, but holographically, this is actually always true. So because A tilde, BB tilde, so let's divide A region A into two parts, AA tilde and BB tilde. So this includes this always this uniton, and there are no overlap here. Then we have inequality of these areas, and then of course this follows. So that way, this inequality is always true for holographic safety. And this is kind of, in that sense, this is kind of analogous to the monogamy of mutual information for holographic entanglement entropy, but this is and not in general true for generic quantum field theory. And so we can look at some explicit calculations. So look like a pure, so simplest thing to do is the ADS-352. So we look at the pure, first one pure, just zero temperature in a Poincare coordinate. So we have this boundary of ADS. This is the extra dimension, z direction. And we pick up region A is this interval and region B is this interval. So this is the entanglement wedge is when they are close to each other, entanglement wedge is this region. So the minimal cross section, it can be computed explicitly in terms of cross ratio of this end points by this formula. And mutual information we can compute at the same time, very simple. And we can compare this by plotting. So mutual information, half of mutual information is always smaller because of previous inequality. This explicitly we can show this. And entanglement wedge cross section as some jump. This is a phase transition point. This is phase transition also true for mutual information. Suddenly entanglement wedge connected. And also that gives actually finite shift of entanglement wedge quantity and monotonically increasing. So anyway, so this is a one explicit example, the simplest case. And we can also look at the BTZ dual to finite temperature 2D CFT. So that case, we have again phase transition, non-trivial phase transition. When A and B, so we choose AB is a boundary. And actually this is not pure because we have a black hole. We can imagine some field double state. This boundary and another boundary, if we sum up, then we get the pure state. That means A union B, rho AB is not pure. But when A is very small, this is just a cross section, minimal cross section. This is a well-known formula. And if A and B gets larger, then minimal cross section actually given by attaching at the tip of black hole horizon. So entanglement wedge cross section has a transition at this point when these two guys are equal. So it just goes to constant because length between boundary and black hole horizon is always stay the same. Constant, but the mutual information is smaller. Half of mutual information gets smaller, but it's monotonically increasing. So this is a holographic computation. Actually, but this group, Brian Swing group and Zarati's group, actually have a very nice computation by using some finite temperature matrix product state. This is we assume some ansatz of tensor network, so we can optimize in a very smaller parameter space. Under that approximation, they find some very interesting results. So this is a entanglement purification versus size of subsystem, like this, size of this region A. So here they actually periodically identified. So if we increasing and going back again, so exactly the same behavior can be seen for even this is a Ising model computation, but some free spin model, but it's different from holographic CFT, but this qualitative feature matches with holographic computation, qualitative. Okay, so, and we can also think about tensor connection to tensor network. So we can give some heuristic derivation of this. So tensor network is the most famous example tensor network which corresponds to the ADS-CFT is Mera. So it's like written here. So it consists of the disentanglers and coarse graining procedures and nicely reproduced entanglement. Or in 1D spin chain, we get logarithmically scaling. And it looks like this minimal surface computation. And so, so this original conjecture of this ADS-CFT corresponds to some tensor network by Brian Swinger. So this Mera network is some time slice of ADS. And so, but there are many improvements of this original conjecture. I don't have enough time to explain this, but there are example famous work by this happy model, perfect tensor network, and random tensor network by Patrick Hayden and Xiao Ranqi collaborators. And so, but anyway, so if we pick a particular tensor network, this gives some graphical way to realize wave functional. And we can compute this number of links, which gives the entanglement. But at the same time, we have some basic principle of how this ADS tensor network corresponds work, which we call surface state duality. So this is my work with Masamichi Miyaji, which is actually sitting there. And so if we pick up some particular region, sigma, and we contract all indices, then we can define some quantum state. So that way, so we can have some, inside the Hilbert space, we can define some quantum state for any choice of subregion. So this gives some very clear picture for how this, holographic correspondence between quantum state and geometry works. And we assume this correspondence below. So this is actually a way to extend ADS boundary towards the inside bulk region. So generalization of this holographic principle. So if we pick up some codimension 2 convex surface, then we can associate some pure state. And for example, we can compute entanglement entropy for this guy, then that should correspond to this minimal length and so on. So if we assume this, then we can naturally reach the same conjecture. So we have region A and region B, and the entanglement wedge is this region, connected region. And this is the boundary of this entanglement wedge, which is a minimal surface, which just connects these 2 points and these 2 points. And we can call this the region C, and this is a minimal cross section. Anyway, so we start with this rho AB, which is defined by tracing this region C. This is just defined by the boundary. This is the original definition of rho AB, but we don't want to change rho AB, but we just change the network. So we the changing network means acting isometry, going this. So we start with this region C here, but we should keep this entanglement wedge region, because otherwise, we lose some information. So in other words, we start with this region C. We squeeze Hilbert space, moving this towards the inside. This always we can do because we just squeeze the dimension by using isometries, and we don't change the quantum state. But finally end at this point gamma AB, because if we go further, we actually going up the Hilbert space. That means we are losing information. We are acting isometry in the opposite direction, so that's not allowed thing. We have to change the state. We don't want to change rho AB. So this is a some termination. We have termination of this procedure at rho AB. This is and rho AB is a really minimal surface. So this minimize this Hilbert space dimension. So that way, if we do this, so maximum compression, actually, after we reach this gamma AB, which is the minimal surface. And after that, what we need to do is decompose this gamma AB. This we can define pure state here, correspond to this region. And we choose A tilde and B tilde separation. We call this A tilde, B tilde. But we can choose any choice of A tilde. We can assume any choice of A tilde and B tilde. But for that, we can just minimize this entanglement entropy. So the minimization corresponds to just a minimization of this area. This is true for standard tensor network description. And then finally, reach the same expression of this entanglement wedge cross section. So yeah, here we assume some optimization within the space of tensor network description. But once we assume holography, we are using this tensor network. So this sounds like a plausible assumption. But anyway, this is a heuristic derivation. Okay, so using the rest of the time, I just want to give some modest result for free scalar CFT, which we are currently trying. So this we'd like to evaluate the entanglement of purification in free scalar quantum field theory, but in continuous way, it's not easy. It's very difficult. So we'd like to use some lattice regularization. So we, for example, we can have a number of total site n. This dot is a site, and we choose region A and region B. We can choose any number of. But here is the simplest case. Number of A and B is just 1, but we can get larger. But for good point of free scalar, free theory is a ground state wave function is Gaussian. So the standard, take standard form, and it's just nicely described by just some matrices which we can compute exactly. And then, so just the computation of entanglement entropy, we just follow the original approach by Bombelli and Colombia. That's quite 30 years ago, actually. So this is just traditional way. So when Hilbert space factorize HA and HB and pure state, we consider pure state described by this matrix, Gaussian wave function, then this entanglement entropy is just computing some eigenvalues of this matrix, which is just component of this E and P, some details. But these are well-defined, well-known way to compute this entropy for numerical way. And then the non-trivial point is this minimization procedure. So for this, we have to add extra Hilbert space H tilde and B tilde. So in general, we have to admit that possible dimensions can be infinite. But let's see what happens after we explicitly analyze. So we have some ansatz of this minimized, some optimized wave function. This again, we assume some. This is also Gaussian. This is sensible ansatz if we assume everything's Gaussian here, but still assumption. And so this anyway, we have this matrix JK, K tilde, this is AB and A tilde, B tilde, and we have to assume anyway we extend the Hilbert space to purify mixed state, but we have to reproduce same mixed state density matrix rho AB. So then this combination just gives some algebraic relation between this J and this previous already known Gaussian wave function. So anyway, so that way, so and in the end, this entanglement of purification can be obtained by minimizing this entanglement entropy for this all of these parameters, JK, but with this constraint. So actually, we tried this computation, and in principle, the problem is that in principle, this dimension of purification space are infinite. However, our numerical analysis actually suggests that finite value of A tilde and B tilde, size of A tilde, actually gives exact answers. We assume, for example, simplest ansatz like A and B is 1, but the simplest minimum value of A tilde, B tilde just 1, and we compute this, and we can extend A tilde 2 and B tilde 2, but still result doesn't change, and precisely analytically same. So that way we expect some, for Gaussian theory, something special happens. And this is our tentative result. And so we compute EOP, we computed numerically both EOP and mutual, half of mutual information. That is always EOP is greater. This is of course should be true, but there's some confirmation. This is a 60 size, but anyway, very small mass. It looks like some power law decay. And similar, this is mass is 0.01. So again, something similar to power law decay. But however, if we take a larger mass, this decay looks like more exponential decay, exponential m distance. This is the distance between this region A. We assume A and B is one side, and they just compute this quantity for as a function of distance between A and B. This is measures correlation, so it should decrease. But this decreasing looks like exponential for massive theory, but massive theory it's like it looks like power law decay. Okay, so these are all things I wanted to talk in this occasion. So let me summarize conclusion. So here I propose this conjecture that gravity dual of this quantity entanglement purification is given by minimum cross section of this entanglement wedge. And there we can think of many future problems, but the direct. So here we assume some free theory, and free theory has some special property. But what's the more general CFT? We assume general safety, and like replica computation, can you compute this entanglement purification and see some matching with holographic formula? And for this, one possible idea is to use our recent developing technique of this path integral optimization. But anyway, so this is a future work. And so also derivation of this holographic formula from just basic principle of ADS-FT is of course very important problem. And so and this also tells us something about tensor network. So can we explore more on the precise description of tensor network, which matches precisely with ADS-FT and operational meaning of this LOCC, LOQ of ADS-FT. And finally, we can think about many different generalizations of entanglement of purifications. There are some work before, power and alpha. Okay, so these are all of my talk. And before I finishing my talk, I just want to advertise our coming meeting program in Kyoto, YITP. So I'd like to also say that we are going to have some long-term program. It's 5 weeks long, but it's a little later. It's 2019, and from May to June. And all of you are very much welcome. And this title is Quantum Information and String Theory. And we are planning to have it from Qubit School and workshop inside in these activities. Thank you very much. So today, so this morning I found very beautiful rainbow in Bariloche. So I took picture this morning. I really impressed by it. Thank you very much. Yeah.
Hi.
So one way to put what you've just done is you found a way to anchor a minimum area surface to other minimum area surfaces and give it a holographic interpretation. Can we iterate this by anchoring more minimal area surfaces to those ones and so on, and still give it an interpretation?
Yeah, that's very interesting question. And if we assume anyway, tensor network description, I think that should be true. Because for tensor, we can cut any part and we can still define pure state and we can define some entropy. And minimization, minimal surface corresponds to minimization of entropy. I think so. But I think nobody so far defined it from quantum information theory side, but it's quite interesting.
Also, your tensor network picture seems to suggest not only you have your conjecture includes the dual for this area of the surface, but also for the choice of the purification, right? So your tensor network suggests that there is a state that lives on these.
Yes. Yeah. So yeah, anyway, we restrict particular tensor network which you described original holographic state, and inside we are optimizing. So that I think exactly that's restricted particular purification. But anyway, we know if we assume that this entanglement rich construction is true, then we cannot change this region. And it's very natural to see if we add any other extra Hilbert space, it's always increasing this minimal cross section at the intuitive level.
Tadashi?
Yes.
If from the definition, it seems like when you need to define this quantity, you add some auxiliary Hilbert spaces, which may not necessarily be the same kind of structure of the theory that you're after.
Yeah.
Why does the answer, do you have an intuition why the answer ends up being a geometric construction in the same space-time? Because say you're doing this for n equals 4 for some subregions, you might think that you append to it some other quantum field theory or some qubit degrees of freedom, and the optimum configuration is not geometric in any obvious sense. Do you have an intuition why it works?
Yeah, that's a good question. And indeed, that's our basic assumption. We can optimize. We just need to optimize within this geometric space. It's a holographic dual. But I think anyway, so one strong motivation why we think that way. So we have this, as already mentioned, but we have some correspondence between reduced density matrix and also entanglement wedge. So we know this entanglement wedge is necessary to reproduce this rho AB. And if we think of minimum entanglement entropy inside, then this minimal cross section is a natural thing to look at. And if we add anything more, we can add some extra degree of freedom. But it's natural that it increases entropy. But this is just heuristic.
So if these surfaces had been, let's say, physical brains, right? And you put a brain that connects them, then they would deform and get closer to each other. Somehow, so I would have had this intuition that these are all very, let's say, some branes which have some tension, which is related to the Newton constant times n-1, and then but somehow your original surfaces are not getting deformed. Is this something we could test in some way? That
yeah, but here again also we take a von Neumann entropy limit rather than linear entropy. So I think back reaction can be negligible. Yeah, like this minimal surface also we don't need to worry about.
That's true, but this is not the back reaction on gravity, but the tension between these branes. And naively, since we take the n-1 limit in both cases, they seem to have naively, I would say they have the same tension.
Yeah, thank you very much. Yeah,
this is a vague thing, maybe.
But yeah, so this is also motivated from this tensor network viewpoint. In that case, we need this part to reproduce this rho AB. And if we have a tension, maybe it gets, you might get smaller area, but then it really go outside, squeezing entanglement weight. So maybe we're losing some information. But yeah, it's very interesting point.
So a simple question, this super additivity you talked about, in general, is it just not proven or is it known to be not true?
Not true. This entanglement purification of generic quantum system don't satisfy strong super additivity. We expect that only true for holographic.
So you mentioned there was an inequality relating the mutual information and the entanglement of purification.
Yeah. These two